Dear professors, I am Junjie Zhang, the speaker of this paper. It is a great pleasure to attend this IASS conference. Now I'm going to interpret and analyze this paper step by step from these 4 parts. This paper mainly focuses on the dynamic failure analysis and a quantitative optimization method for the memory sections of singular reticulated domes. Before establishing the model, we should confirm the specification in accordance with the relevant standards. Among them, the static safety factor K should be greater than 2, and the maximum deformation in dynamic safety should be ensured to be less than 1/400 of the span. This model is a cavity 8 singular reticulated dome. The parameters have been shown in the table below, and the model have been shown in the figure to the right. The location of the dome is chosen in Mianyang, China, and the various parameters in the table are determined according to this specification. Then we select 3 suitable seismic waves, named Improved Valley 2, Improved Valley 6, and Superstition Hills 2. Then the loads that should be applied on the dome and their combined value are determined according to this specification, which are simulated as nodal masses applied on the dome uniformly. After the model is established, we performed static and dynamic safety analysis on the dome. The results show that the value of both are in accordance with the regulations. The K is larger than 2, and the maximum deformation are less than 0.1 meter, namely the 1/400 of the span. Then we increase the acceleration amplitude of each seismic wave and investigate the maximum nodal displacement under each PJ value. Through this curve, we can find the inflection point of the curve and can choose the 990 as the critical failure load under the Improved Valley 2. And by using the same method, we can obtain such value of Improved Valley 6 is 1260 and Superstition Hills is 830. After inputting these 3 seismic waves, we can obtain these 3 information: the time history curve, the deformation shape, and Mises stress distribution of the dome. Same as the Improved Valley 6, and also as the same. Through the time history curves, it can be seen that the failure process and characteristics show some similar phenomena. The development can be divided into 3 or 4 phases: the stabilization stage, critical stage, and failure stage. Here, the deformation of the dome is enlarged by 7 times. It can be seen that the members that have large deformation are mainly concentrated on the diagonal members of the peripheral frequencies, which can be regarded as the weak part of the dome. The second major part of this paper is the optimization of the dome in order to achieve a better dynamic stability. A preliminary design of the dome is firstly carried out. We focus on 2 ratios, namely area ratio and radial ratio, where the area ratio is the ratio of the section area of diagonal members to that of longitudinal members, and the radius ratio is the ratio of diagonal members' radius of inertia to that of longitudinal members. We use AR to represent the area ratio and the RR to represent the radius ratio. So, taking the rise to span ratio of 1/3 as an example, we designed 20 different cross-sections of the dome and record their corresponding data under the action of Improved Valley 2, with a guaranteed static safety factor greater than 2. 3 indicators, omega maximum, self-weight, and E maximum, are chosen to observe their relationships with such 2 ratios. As the same method is used for the dome under the rise to span ratio of 1/3 to 1/9. By observing the changes of the curve, we can make a first choice of the more optimal combination. First of all, we can find that number 11 and 12 are guaranteed to have a lower self-weight, lower deformation, and also a lower strain energy. However, during the analysis, it is found that the rigidity of the dome in these cases is very high, and the dome is more likely to collapse as soon as it breaks, which are not reasonable designs. And similar phenomena occur in the cases of other right-man ratios. Secondly, number 8 and 9 are the smallest self-weight. However, their deformation is larger. Also, they are not better choices. After comparison, we think number 5 is a good choice. With the same method, we can choose other optimization solutions under other right-man ratios. After that, we fit these two objective functions. And by using these two functions, we can obtain the data calculated by these functions for each combinations and be able to select the more optimal combinations. As shown in the table to the right, it is possible to conclude that making the values of the two objective functions close to 1 at the same time can give the dome a better dynamic performance and reduce the steel consumption and engineering costs. At the end of this paper, we give several conclusions as follows. We summarize the weak part of the dome and its deformation development law under dynamic action, and give a preliminary quantitative optimization method for the member sections of the dome. These are our main work and the main content of this paper. Thanks again for your patience.